Alexander Grothendieck had once said, if there is one thing in mathematics that fascinates me more than anything else, and doubtless always has, it is neither number nor size, but always form. And among the 1001 faces whereby form chooses to reveal itself to us, the one that fascinates me more than any other and continues to fascinate me is the structure hidden in mathematical things. So let's dive into this world of structures and form. Let's dive into category theory. Let's assume I'm a 15-year-old. I'm in high school. I have no understanding of advanced mathematics or physics. How do you explain category theory to a 15-year-old? Dumb it down for me completely.
All right. Well, first of all, thanks for this quote. I didn't actually know this quote. This is an excellent quote concerning what we're going to talk about. Yeah, so what is category theory? So let's see. You may have to give me some feedback about, when I'm close to this 15-year-old, when I'm getting further away.
That's my mental age anyway. So
no, very good, yeah. But it's exactly about this. It's a form of simple mathematical formalization of the idea of structuralism. And we can make this very easily, very precise. So let's assume we're happy with the notion of a set. So a bunch of things of a given kind. And in math, and that's good, there's lots of sets that we can think about, but we want to be thinking about for the moment to get our, to tip our toes into the water, let's think of sets of mathematical structures. If the 15-year-old maybe knows what a vector space is, or maybe
I've heard of it.
Or a space. Let's just say, or a vector space, Can we think of the set of vector spaces, or the set of what would be a better example? Maybe spaces, is that a good thing? Like topological spaces?
What do you mean by a set of spaces?
So I mean the class of them, like the collection of all of them. So
all the spaces in the world, combine them together into a group, that gives you a set of spaces.
Yeah. So we're really just talking about the concept of a space, and we envision that we kind of embody this concept by just having all of its instances collected in a set.
I follow.
So we're talking about large sets here, which are really called classes, but let's just say set for the purpose of this discussion, right? But some of the sets we'll be talking about will be large. If some logician listens to this podcast, they should think of classes, but we'll just say sets. Okay, so there's a set of spaces. So a sphere, the two-sphere is a space, or the plane is a space, right? Or a cube is a space. These are different spaces. Or a universe is a
They're all members
space.
of the set.
Yes. Okay. And so now, for the most part of the development of math, we would be talking about the set or class of these spaces. So they would all just be sitting there as sort of little points. We envision this point cloud. You think of a finite set. You think of each element as like a point. You put them all in a bag, and now we have this bag full of all spaces are in this bag. But we don't, the bag doesn't remember the fact that these spaces have internal structure, right? It just says, here's one space, here's one space, here's one space. But the whole point of a space is that there's something that makes it the structure of a space. It has some structure different from other things. And so the idea of category theory is really, or the idea of a category, let's say, is to just remember a little bit more than just this set of these objects, as they're going to be called. So these elements, these spaces, we're going to call objects. Just a word. And so we say, well, let's also remember, since there is some structure around, let's just remember how these objects relate to each other. Right? Spaces may have some relation to each other. How do spaces have relations to each other? Well, simply or concretely by the fact that there's maps from one to another. So, for instance, I have the point space here, which is just a point. And I can consider a map from the point. So here's another space. Let's call it X. I don't know what X is like, say. Maybe you handed me X, and I need to start exploring.
Mystery space.
Exactly, mystery space.
Okay.
And now I want to start exploring. What is it, actually? What did you just hand me? So how do I go about this, actually, literally? And this is a very, how should one say, operational, physical thing. Like physically, how do you see space? Well, you actually probe it by sending photons into it, right? In a way, so we don't know actually the space either that we're living in. We probe different parts of it and build a bigger picture of it. So the same we can do now abstractly with this space X. And we have our point space here. So I want to start probing my space. What can I do? Well, I look at maps, continuous maps as it were, from the point to X. And what is such a map? Well, this point has a single element. And so this map will take this single element to some point in my space. So a map from the abstract point to X is just a point in X. Okay? So by looking at all the maps, the set of maps from the point to the space X, I know suddenly at least all the underlying points of X. So of course, what makes a space, a topological space, a space is not just that it has underlying points, it also has some continuous structure, the encoding how these points cohere to each other. They're kind of bound to each other by open subsets. But at least now by looking at this Hom set, as one says, is a set of maps from the point space to X, that Hom set is the set of points of X. So now I've learned by looking at maps between spaces, I've learned about the inner structure of X. But of course, as we just said, X has more, in general at least, it might be a discrete space. If it's a discrete space, that is all there is to it. It's just a set of these points. But usual spaces, for instance, if it's a two-sphere, of course, these points, they are glued together in some continuous way. So how can I start detecting this? Well, let's detect with let's probe it with a slightly more sophisticated space. Instead of just taking the point, let's take the real line, or if you wish, envision an interval. Just a one-dimensional space that is a continuum line.
This is a separate space, right?
Yeah. So we
had the point, we drew all the maps from the point, done. Now we have a line.
Yeah, now we look at the line. Yeah, so here's a mystery space X, but there's also some spaces which we can name right away. The point, the line the plane,
right,
3D space, and so forth. So we kind of have these under control. We can write them down by saying this is what they actually consist of. So now we say, well, let's look at all maps from the line, the abstract line, the continuum, as it were, right, into X. Well, what does this give us? It gives us the continuous curves of points in X. And so now we learn by looking at all these maps from the abstract curve into X, we find the actual curves, the continuous curves in X. So we learn a bit about how points hang together. For instance, we might observe that no matter how we map the line into our space, we can always find 2 points in our space that will never be sitting on the same line. Suppose that happens, then we have learned that our space actually has it has 2 distinct path-connected components. It's actually the disjoint union of 2 disconnected pieces. For instance, our space may have been not just the two-sphere, but 2 copies of the two-sphere next to each other without relation. That might have been the space. It's also a space. And so so the 2 copies of the two-sphere is not path-connected, as one says. And it's exactly in this sense that if you have a path of points, being this curve, you can never connect 2 points that sit on distinct copies of this space, which is the disjoint union of the two-sphere. So you can already see by mapping different spaces into our space, we learn about the inner structure of that space. And now it's easy to envision that you can just keep going. Next, you map all the abstract plane into X, and then even more complicated spaces. The more spaces you map into X, the more you learn about the inner structure by some relational sense, in that you keep relating your space, mystery space X, to these given default spaces.
These probes that you're sending.
Yeah, exactly. And so it seems intuitively plausible that it should be possible to completely understand X if you knew all these mapping spaces, or these mapping sets, these Hom sets, from all other spaces into it.
If you knew all the maps that existed for X.
Yeah, for any other space. So if you knew all its relations in every other space. And that turns out to be the first little fact. This is the Yoneda lemma, actually, of category theory, that this is actually true, right? So, but to say this now, first we should say, what is a category? So the idea now of a category is a really clever idea, right? You want to say, well, we want to have this set of all spaces, but it should know about the inner structure of these spaces. Now you might do this in a boring way. You say, okay, let's just kind of note for each space its inner structure, just write it down. But that's a very boring and inelegant way of doing it. Now we just saw, well, no, the inner structure is encoded in this relation to other objects of a category, which are embodied by these maps. So let a category just be a set of objects together with, for any pair, a set of maps, a set of things that we're going to call the maps between these spaces. So in our example of the topological spaces, we actually know what the maps are. They are predefined. We know what a continuous function between topological spaces is. But we're going to abstract from this and say, a general category might just be, you have this set of objects that it consists of, and for every pair, you have a set of maps to be defined thereby. So you don't know yet what these maps do. But that's the first clever observation, that you don't have to know this in advance. This is implicitly encoded. So all we need to add now is that these sets of maps, they should have some minimum consistency to actually behave like sets of maps. Right? They should not just be any sets. To be sets of maps means they have, for instance, the property that if I have the set of maps from space X to Y and the set of maps from space Y to Z, then clearly there should be some way of some composition operation that takes a pair of such maps, X to Y, Y to Z, and forms a map from X to Z, composing them. So we demand that we have sets of maps and this composition operation whenever they are composable. So whenever the target of the first map is the starting point of the next map. And then we just demand that this composition is, in the evident sense, in quotation marks, associative and unital. So we just demand that it behaves like a composition is.
Where are these demands coming from, these laws?
So these laws are now the definition of what a category is. So we're going to say that, right?
But is that an arbitrary law that you're putting in place? Where do these laws come from? Is that necessary because otherwise the category just falls apart?
Well, so, right, yeah, as we said at the beginning, of course, we're making up axioms here, but these turn out to be good axioms. We do want, right? So remember what we were trying to do? We were trying to find a mathematical formalization and formulation of this idea of remembering the structure of objects by remembering their relation to each other. So that's what we are after. We wanted to say, what does it mean, relation to each other? And it's relation, there's also another sense of mathematical relation. That's not what we're talking about. We mean relation in the sense of maps, one thing probing the other, right? And so we're just saying, okay, how do we axiomatize this abstract idea of maps? Well, and we just said, well, maps, first of all, they should exist for any pair of objects. They should be composable. And then, if these behave in any way like actual maps, then clearly if you compose three of them, it shouldn't matter whether you first compose the first two or the last two, right? So it's just out of that observation that we make up at this point, of course, this axiom that we say it should be associative, because then it does feel like having actual maps. You see, we're doing quite an abstraction step here. We're saying we can take any collection of sets between ordered pairs, declare the map. Well, we need to add a little bit of consistency condition for that to actually behave in any way like a map, because these sets are not actually defined analytically as maps of anything necessarily, right? So we just impose conditions. We say it's like a synthetic way of going about math. We say we want to define a duck. So instead of giving you the cellular decomposition of a duck, we say, well, it should walk like a duck, quack like a duck. This is the standard slogan, and that's what we're doing here. So we're saying a set of structural objects, it should walk like a duck, so it should look like a bunch of objects with maps between them.
Because if you don't put those constraints, then anything could be a duck, right? Then everything falls apart. Okay.
So that is a category. It's a set with this extra information of what are the maps between its objects. Where if we think of this set as being a set of ordinary mathematical structures, like vector spaces, Lie algebras, Lie groups, manifolds, number fields, then these maps are the evident homomorphisms, as they call the actual, because then these objects we're talking about themselves consist of sets of points with some extra structure, and the maps are just the maps that map these points around, preserving that extra structure. But now the first, insight of category theory is that we can be more abstract about it. What we just said, the examples we just gave, Lie algebras, vector spaces, are called concrete categories, but there's non-concrete categories where the would-be maps, they're not actually called maps, they're called morphisms or homomorphisms.
That's just another word for the maps.
Just another word for these maps. You should still think of them as maps, but they may no longer actually be maps in the operational sense that map points around. We can give an example maybe in a moment or maybe now. Yeah, maybe it's a good time to give an example. So here's a simple example of a non-concrete category that will be useful for several aspects that we maybe discuss later is BG. BG is a very nice category. So think of a group. So let's see, the 15-year-old, does he know what a group is? A symmetry group?
No, I don't know.
Okay, so all right, we need to know what groups are. So let's talk a bit about groups then. So groups this is not category theory, but it plays a big role in category theory. So all right. Well, okay, no, we have set up the machine to really talk about it. Let's suppose some category. We're looking at some category. And by the way, of course, we should maybe highlight that's the word where the word category comes from, or what it alludes to is this idea of categorizing things of a certain joint structure, right? Space. All right. So let's suppose we have some category. And now we pick an object in there. And now, as we just said, we also know all these maps from this object or to this object. In particular, we know the maps from this object to itself. And now we can look at those particular maps from the object to itself that are actually invertible in the sense that, so a map is called invertible if it goes from x to y. If you have another map that goes from y to x, such that the composite is actually the identity map on x. It does nothing, and vice versa. So it has an inverse. You can undo what the map did. It does something, but you can undo it. So it doesn't forget anything in a way, and doesn't add anything. It just kind of reshuffles the structure.
Even after all those transformations, you've come back to the same point.
Yeah, right. And so now, for every object in our category, we can look at the collection of all the maps from the object to itself that are invertible. So if we realize this in our example of topological spaces, these are called the homeomorphisms. A map from a topological space to itself, so it kind of reshuffles all the points, but in a continuous fashion, and such that you can undo it. So it does some kind of twisting to the space, but you can undo it.
It preserves itself.
Yeah. I mean, there's easy examples. For instance, let's take the circle. It's a space, and there's a map from the circle to itself, which kind of rigidly rotates it around. It takes every point here to the same point, but rotated by some fixed angle. So that you can clearly undo by rotating back. So this collection of endomorphisms, as they're called, of maps from an object to itself, have the special property that you cannot forget for the purpose of the further discussion all the other maps around. Just focus on this. These maps form a little universe in themselves, and that, well, you can, if you have one, you can always compose it with another one, since they both start and end at the same object, so they're always composable, and they're invertible. And there is, among them is always the identity map. This is one of the axioms which we maybe didn't mention before, but there's always, we always wanted to say one of these maps is the one that doesn't do anything.
Stay where you are.
Yeah, right. Exactly. And so that is called a group. This is short for, historically, there was a group of symmetries, right? So every such invertible endomorphism is called a symmetry. We saw it in the example of, maybe better than the example of the circle is to take some polygon, take a triangle, then let's regard it not as a topological space, but as a graph. So let's remember that it has these 3 vertices and 3 edges, and let's demand that in our category of graphs, the allowed maps have to map the vertices to vertices and the edges to edges. So then what you can do to a triangle is you can have to send the points. Each point has to go to one of the points, but you also have to respect the edges. So actually, you can just, you can rotate the triangle by angles of 2 pi over 3, and you can, I suppose, reflect along.
Invert the image like a mirror image.
Yeah, right. So we get a group that's called a group of symmetries. So these are the symmetries operations of a triangle. If you look at a triangle, you see how it has symmetries in the sense that, well, you can, some operations on it that don't change it. And there are several of these operations, and that's why people call it a group. It just means a collection, a bunch of. There's all these mathematical terms for a bunch of things. Sheaf, heap, shoba, group. It's a bit crazy. Anyway, group is short for group of symmetries. And so we just learned, actually, that this is a super general idea. Any category, any object of that category has a group of symmetries, called its automorphisms also. It's those maps from itself to itself that are invertible. All right. So we already see now. So what we did, we had a possibly very large, in the technical sense, category, but we looked now at this single object and all the morphisms from itself to itself. Now let's forget the rest of the category. We've actually found a new tiny little category. Namely, and this is no longer concrete. Well, you see, it's a simple category. It has a single object. It's the category of this one thing. Right? So like an object, or what you think of as an object, can sort of belong to different categories depending on what you think of it. Like we just saw with the triangle, you can think of it as a graph, you can think of it as a topological space, you can think of it as just a plain set of points. So same here, like for every object, you can think of it as being in the category of that object, right?
It just contains itself.
Yeah, just itself.
The singleton set.
Exactly. And as such, it still has these maps, though, which remembers how there's still some internal structure in there, these symmetries. And so the group of these symmetries, because it's called group, it's always abbreviated as G. So we would like to call groups, the generic group is always denoted G, like the generic space is always denoted X. So G. And so we need a name for this abstract category that consists of a single object and whose morphisms, whose maps are labeled by, one says elements of a group, so are labeled by symmetries of something. And the composition of the maps is just given by as one says, is the group operation, the original. So this category is called BG for historical reasons, but that's just what it's called. And so we found a new category that is not, because we forgot now that this object, it may have been originally a topological space, and we could see that it was a topological space by homing these other objects into it and seeing its internal structure. But now that we forgot everything else and just isolated this thing, there's nothing else around for the hom into it, so it just has become an abstract point now, this thing that maybe have been a topological space to begin with. Could be anything now, and this group is acting on it. Kind of, it's the abstract incarnation of this symmetry group acting on something. So that is a non-concrete category. Very simple one, a very important one.